Hi everyone, we're off to chapter 8, which is called confidence intervals. So we'll start with a scenario here. Suppose you work for Spotify and you're interested in the number of songs a user listens to in a week. So you conduct a survey and calculate the sample mean, which we use X bar as the symbol for the sample mean, and the sample standard deviation S. So X bar is a point estimate for the population mean mu, and S is a point estimate for the population standard deviation, sigma. So X bar and S are statistics, mu and sigma are parameters. We learned that back in chapter 1. Okay? This chapter, we're going to use some sample data to make generalizations about the population. So this part of statistics is called inferential statistics, where you take a sample and you infer things that you think are true about the whole population. So we can infer the mean of the population as X bar, but that's not very likely to be the case. So we're going to use what we call a confidence interval, which is another type of estimate, but it's an interval instead of a single number. So it provides a range of numbers in which the population mean is expected to fall. We cannot be 100% certain the population parameter falls within the interval, but we can get pretty close. All right, we're going to change gears. I talked about population mean and the point estimate, which is the mean, but this one deals with proportions. So it says this: 32% of Americans believe guns should be allowed on college campuses, with a margin of error of 3%. This one deals with proportions, not means. So the confidence interval is going to look like p hat minus EBP and p hat plus EBP, where EBP stands for the error bound for proportion. This change is based on the confidence level, which is how certain you are that the population parameter actually falls in the interval that you found using your sample. Okay, the higher the confidence level is, the wider the confidence interval would be. So in this case, we do 32% minus 3% and get 29%. 32 plus 3 is 35. So what is implied in this one is we are 90% confident that the actual percentage of people who believe guns should be allowed on college campuses is between 29 and 35%. Alrighty. In the prior example, the point estimate 0.32 represents a proportion, not a mean. We use p hat to represent a point estimate for population proportion. Alrighty. Alright, let's switch gears back to the mean. If we want a confidence interval for means, we'd use X bar minus error bound for mean and X bar plus the error bound for mean. Okay, the error bounds for these guys we use by finding the Z number of our sample there, or the Z number of the confidence level, and multiplying it by sigma X over N, radical N for means, and radical P hat Q hat over N for proportions. Alrighty. Q hat, remember, is 1 minus P hat, so that's going to come into play later. But you see the error bound for mean, Z alpha over 2 times sigma X over radical N, and error bound for proportion, Z alpha over 2 times P hat Q hat over N. We're going to talk more about Z alpha over 2 coming up. For now, all you need to know is how to use the calculator to find these confidence intervals, all right? And as you can see on my next sentence, that's what it says. Luckily, our calculator is equipped with confidence interval functions. There are 3 functions we will use in this chapter. The first one is Z interval. We use that for when sigma is known. Okay, sigma is known, we're going to use Z interval. T interval, we're going to explain what the heck that is in a minute, used for means where sigma is not known. And then if we're dealing in proportions, we're going to use 1 prop Z int for proportions. All right, so let's do a couple of examples where you know sigma. You measure 21 textbooks weights and find they have a mean weight of 35 ounces. Assume the population standard deviation is 10.2 ounces. Ding, 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 everyone. We know this population standard deviation. So we know that. So therefore, we're going to use Z interval. Alrighty. We want to construct a 90% confidence interval for the true population mean. Alright, so let's go through the steps here. We're going to go second stat, and I believe it's in the test menu. There you go. It's in the test. We want Z interval. So we go down here to Z interval. And then we want to input the data. Nope, we want to input the stats. There's going to be an example where we're going to input the data later. Okay, so our standard deviation was 10.2. Whoops, not 10.5, 10.2. And then our X bar was 35. We got a sample of 21 textbooks. We want to be 90% confident. Okay, 90% confident. And we calculate. So there, chances are, with 90% confidence, we say that the average weight for textbooks is between 31.339 and 38.661 ounces. That's what that is saying. All right, we're 90% certain the actual population mean lies between those two numbers based on that sample of 21 books we took. Okay, so that is how you use your calculator to do that Z interval. You can find the error bound for mean because MyOpenMath is going to ask you, what is the error bound for mean? So you don't want to have to do that Z alpha over 2 times sigma x over radical n. You don't want to do that. You want to do this right here. You just take the top number, subtract off the point estimate, and there's your error bound for mean. It's basically half of the length between those two numbers. Okay, that's going to be your error bound for mean. All right, let's do another one. You measure 25 turtles' weights, and they have a mean weight of 61 ounces. Assume the population standard deviation is 12.4. Based on this, what is the maximum error for a 95% confidence interval? So they're asking for the error. They're not asking for the confidence interval, but we're going to find the confidence interval anyway, and then we're going to take the high number and subtract off that 61, which is that point estimate. So I run through the same exact calculations with Z interval, and you see that the confidence interval is 56.139, comma 65.861. So I take the 65.861, subtract off the 61, I got 4.861 is my error bound for mean. All right. You may also see a confidence interval listed as this X bar plus or minus EBM. All right. And I think the next example is going to show that. So now we're going to look at a couple of examples where we do not know the population standard deviation. Well, in that case, we have to do a different calculation, and we use the student's T distribution. So for more information, look up William S. Gossett, who worked for the Guinness Brewery in Dublin, Ireland. So it takes into account the sample size and uses what we call degrees of freedom, which is n-1. All right, the main goal for us is using it when sigma is not known. That's pretty much all you have to know. You have to know when to use the T interval and the T test, all right? You don't really have to realize and understand where it came from, where that distribution came from. You just need to know how to use it. All right, let's do this. A researcher is finding that a 95% confidence interval for the number of times per day that college students text. The study included 116 students who averaged 42.2 texts per day. The standard deviation was 24.2 texts. Find the confidence interval. So sigma is not given, S is, right? They give you that the standard deviation for the 116 students was 24.2. All right, so let's do it. We're going to go over here. We go second. That is wrong. We go second stat. No, we just go to stat tests. All right, then we go down to T interval. because we do not know the population standard deviation. We're going to do stats in this case because we're not given the data. X bar was 42.2. The standard deviation was 24.2. And we surveyed 116 people. And we want a confidence interval of, or a confidence level of 95%. That's going to give us the confidence interval then. We calculate away, and there is our confidence interval. So, with 95% certainty, we can assume that the population mean, so the mean number of texts that college students send is between 37.749 and 46.651 per day. All right, the mean. Certainly you're going to have some students that text 500 times per day and others don't do it at all. All right, okay. Let's switch gears now. Oh, let's keep on the T interval. So a psychiatrist is interested in finding a 95% confidence interval for the ticks per hour exhibited by children with Tourette syndrome. The data in the table show the observed ticks in an hour for 10 children with Tourette syndrome. What is the confidence interval? Okay, you are not given sigma, so we're automatically bling, ding, ding, ding in your head, T interval, right? And we're given a set of data, we're not given the stats. So when I do the calculator, I'm going to need to go to stat edit, and I'm going to need to put those in my calculator. Remember, if you have something in L1, you could hit the up arrow, hit clear, and then enter, and then you would get rid of what's up there. Okay? So here we go. I need to put my 10 numbers in there. So 91488, 91488, and the other 5 are 111611 111611. Hey everyone, if you get the wrong answer in my open math, it could quite possibly be that you entered one of these incorrectly. So always go back and check your list, all right, to make sure you entered them all correctly. Now here we go. Now I'm going to go to stat, tests, and I'm going to go down to T interval. This time I'm using data. So I go over to data, hit enter. It wants me to use L1 with a frequency of 1. Right? If you put a frequency distribution, so L2, for instance, held the frequencies, then you'd put freq as L2, right? Okay. Confidence level, we wanted 95%. So there you go. Calculate away. And then you have 3.6436 to 8.9564 is your confidence interval. Oh, well, I got it totally wrong, didn't I? Something is incorrect then. Oh, 0.98 I used in my notes where it says 95%. Okay, so hopefully everyone watches the video because I did it wrong. In my notes, I did 0.98 where I was supposed to use 0.95. As you can see, the 0.98 confidence interval is wider, right? If you want to be more confident, you got to bring more numbers in to be more confident, right? Okay, so that's how to do it with data. Let's turn our attention to confidence intervals for population proportions. So we're going to use the 1 prop z int for these. So a phone manufacturer is interested, oops, sorry for the typo, interested, I don't know what that means, interested in constructing a 99% confidence interval for the proportion of phones that break. 94 of the 1067 randomly selected phones break. What is the confidence interval? So we're going to use the 1 prop z int for this. These are pretty simple inputs. So we go to our calculator. We're going to go stat over to test. We want 1 prop z int. Sometimes it's better to use the up arrow, go around the horn like the slotted pig in Toy Story. So 1 prop z int, enter, and then I have my x value is going to be 94. My n value is 1067. And my confidence level, what do we use? 99 in this one. 99% confidence level. So we're doing a 99% confidence interval then. Hit enter, so there you have it. So 6.58% and 11.05%. There's your confidence interval. Alrighty. So with 99% confidence, we could say the proportion of phones that breaks is between those two numbers. If we want to express this confidence interval in the form p hat plus or minus EBP, first thing we got to do is we got to find that EBP. Well, the EBP in this case is just going to be the half the length of the interval, right? Because the midpoint of it is going to be the point estimate. So we find the midpoint by adding up, dividing by 2. We got 88.1%. Okay, so that is the point estimate. That goes right here. And then I could do 96.9, the upper end minus the point estimate. 8.8% therefore is my error bound for proportion. So then this confidence interval here could be restated like that right there, okay? Based on those calculations. Now, everyone, we come to the trickiest part of this whole lesson, calculating the sample size n. A lot of times people are wanting to get a particular error bound, so they need to figure out how many people need to be in their sample or how many items need to be in their sample to achieve the error bound they want. All right, so the formulas right there, n equals z alpha over 2 squared times sigma squared over EBM squared. That's for population mean. Population proportion, z alpha over 2 squared times p hat times q hat over EBP squared. Okay, the z alpha over 2 is going to be calculated the same way. We're going to use inverse norm to calculate z alpha over 2. So the first thing you need to do is figure out what this alpha value is. So if you have 95% confidence interval, you're going to take 100% minus that 95%. You got a 5% alpha value. Okay, so that means that the two tails, right? That means the two tails here, these two tails got to add up to 5%, right? They got to add up to 5%. So guess what? They're each going to have 2.5%, right? They're each going to have 2.5% in them. All right, so the alpha over 2 value, therefore, is 2.5%. And therefore, when we do z alpha over 2, we're going to use a left tail area of 0.025 with the mean of 0 and the standard deviation of 1. And there's going to be your z alpha over 2 value in this case. So each of these problems starts with calculating that z alpha over 2. All right, so let's look. A political candidate wants to determine what percent of people support her. If the candidate wants a 5% margin of error at a 99% confidence level, what size of sample is needed? So this one deals in proportions, so we do the proportion formula. Note, we are not given p hat in this case, all right? A lot of the problems you're not going to be given p hat, all right? When this happens, just assume p hat equals 0.5, okay? Then q hat is going to be 1 minus 0.5, which is also 0.5, all right? So 99% confidence interval implies alpha is 0.01. So that means alpha over 2 is 0.005. So inverse norm, you're going to put 0.005 as your left tail. All right? And you're going to end up coming up with this number. I'm going to show you the easiest way to make these calculations on your calculator. Not given p hat or q hat, so we use that. The error bound for proportion is 5%, so I'm going to use 0.05. Okay, so And we're always rounding up on these, everybody. Always round up. So here we go. Off to our calculator. And I want to do inverse norm first. That's going to be under the distra menu. So I go to inverse norm, and I'm going to go an area of 0.005, mean of 0, standard deviation of 1. It uses that standard normal distribution to find that z number, right? Z number implies a standard normal. That's why mean 0, standard deviation is 1. Okay, paste and enter, and there is your z number, your z alpha over 2. Now we have to multiply that by, or we have to square that, multiply it by p hat, multiply it by q hat, and then divide it by the error bound for proportion squared. So all I'm going to do, everybody, if I just hit the x squared button right here, whenever you hit some operation with this flashing guy here, it's automatically going to take the prior answer and it's going to do the calculation on that prior answer. So if I hit x squared, it takes that last answer squared. All right? Or if you don't like that, you could do this. You could say, okay, I'm going to choose this and I'm going to square that. The problem with that, though, is you're squaring a negative and your answer is going to be negative because your calculator is going to square the 2.57 first, then apply the negative number, okay? So what I would do, I would just do x squared, answer squared, okay? Then times p hat times q hat divided by error bound for proportion squared, and enter. You come up with 663.49. Always round up on these, so I'm going to round to 664. All right, last example, y'all. This is a long one, long chapter, right? You want to obtain a sample to estimate population mean. You believe that sigma is 70.1. You would like to be 95% confident that your estimate is within 2 of the true population mean. So that means our error bound for mean, right? Our EBM is 2. Our sigma is 70.1. And we just have to calculate the z alpha over 2 number. 5% confidence interval, so alpha over 2 is 2.5%. Let's do this. Off to our calculator. We go second, distra. I'm inverse norming. 2.5%, so 0.025. Oopsie. Leave mu and sigma the same. Okay, 2.5% is going to be a lesser number. I see negative 1.96 is not as far from the mean as negative 2.58 because we're not as confident in this case. So the band is going to be a little bit smaller for the confidence interval, right? Now I got to multiply, I got to square that, so x squared times sigma squared. Sigma is 70.1. And then I divide that by error bound for mean squared, which is 2. So divide it by 2 squared. Enter. So 4720 is what we are going to enter for our sample size in MyOpenMath. We would enter 4720. Okay? There are 3 homework assignments for this chapter, but y'all a bunch of smart people, you can handle it. We'll see you in the next chapter. Bye-bye.